one of the things you can do is look at the redox chart. When you get the redox chart, which species is the most electron rich on the redox chart? You know? Which one? Yeah, the strongest reducer, the most electron rich, which is? Lithium metal. And so that's one way. If all these occur on the chart, then we would just pick the strongest reducer out of all of them, and that would answer the question. But most of these, in fact, none of these occur on the chart, so we'll have to figure it out in a different way. And so if you're interested in redox properties, then the most useful tool to analyze the composition, the formula, is oxidation numbers. You will be given the redox chart on the exam. So there are different ways we can analyze the oxidation states. And one of the ways is we just follow the rules, the steps that are given in chapter 3. And for these, that's probably the easiest way to do it. And so I would just do this. Put this. So we go to phosphate here. What do we do first, phosphorus or oxygen? Oxygen, and what's the oxidation state of oxygen? -2? -2 is correct. So it's -2, and we could set this up. We can do multiple rules here. 4 times -2, because we have 4 oxygens, is equal to -3. And so we need to know what X is, the oxidation state. So we have 1 times X plus 4 times -2 is equal to -3, which means phosphorus is going to be +5. And then oxygen is -2. Usually, if you forget the rules, usually what we do is we assign the more electronegative species its preferred oxidation state. Oxygen likes to gain 2 electrons, making it a good oxidizer. You know, oxidizers take electrons. Oxygen wants to take electrons to get an octet, which we say, or the same number of electrons as neon. That is 10 electrons. But we have to know, it seems like maybe this is electron rich, you know, because oxygen. Doesn't it seem like oxygen is electron rich? But the case is it's not, because oxygen wants to have 2 electrons. So what we have is we have electron rich, electron poor, and then something in between. And that something in between I just call electron happy as is. So oxygen is happy as is because it wants those 2 electrons, because then it's like neon. So you can tell if something's happy as is it's based on stability. And so what we do is we look at other compounds in which oxygen is -2. So one of the compounds that oxygen is -2 in is water. Water has oxygen in the -2. And then if we think, if water is electron rich, then some oxidizer can come along and oxidize this, the water. When we come along and oxidize the oxygen in water, we form oxygen gas, O2 gas. So is it easy to oxidize water, or is it hard to oxidize water? It's pretty hard to oxidize water. Oxidizing water is tough. And so what we say is it's pretty stable. And so that must mean that a -2 on oxygen is happy as is. But then you go over to the hydrogen. We look at it by atom when we do this. You know, and so we go over to hydrogen, and we might go, Well, oxygen might not be electron rich, but isn't hydrogen electron poor? Doesn't hydrogen want to oxidize something? Shouldn't water be a good oxidizer? If hydrogen oxidizes something, then it forms hydrogen gas, elemental hydrogen. And so does water oxidize a lot of things to form hydrogen gas? No. And so that must mean a +1 oxidation state on hydrogen is happy as is. It's fine. It's not that bad. If it were bad, then it would be more reactive. Well, then we go to phosphorus, and we think about phosphorus. And what's the range of oxidation states for phosphorus? If we look at the periodic table, we can see the range of oxidation states here. Let me pull up a periodic table here. This time I'm just going to use a Chem 4 periodic table. So the range of oxidation states we get based on gaining electrons to be like argon, or losing electrons to be like neon. And so we can either gain electrons, because the noble gases are quite stable. These are very unreactive, so there's something special about having the same number of electrons. And so how many electrons would phosphorus have to gain to be? Well, it has 15. It would have to gain how many to become 18? 3. And each extra electron is negatively charged, so it's -1, -2, -3. So on one end of the range, we have -3. At the other end of the range, we have, well, going from 15 to 10 means losing how many? 5. So if we lose 5 electrons, it's 5 negative charges that are no longer there. The number of protons stays the same, and so we end up with +5. So the range of phosphorus is between +5 and -3. On the +5 end of things, we call that electron poor. On the -3 end, we call it electron rich. And so in phosphate, we're electron poor. For sure, we're electron poor because that's +5. But +5 means different things for different elements. So for example, a +5 on nitrogen is unhappy. It's quite reactive. Like nitric acid. Nitric acid is a nasty acid. It's quite reactive. And so we try to stay away from nitric acid. However, what about phosphoric acid? Is phosphoric acid as nasty as nitric acid? And it turns out it isn't. There are different reasons for that. One, nitrogen with a +5, it's a small atom. A small atom with a +5 is going to be much more reactive. It's going to have much higher charge density than a phosphorus. Phosphorus is a lot bigger, has a whole other shell of electrons on it. And so phosphorus at +5 isn't nearly as reactive. And therefore, we see on our redox chart, we see nitrate, but we don't see phosphate. You know why we don't see phosphate on our redox chart? It's not because it's not common. Phosphate's quite common. It's used in laundry detergents and other things. So phosphate's really pretty common. The reason it's not on the redox chart is it's kind of weak or kind of strong. It's kind of weak. And so it doesn't appear on the redox chart because it's kind of weak and it's not very reactive. And so +5, you would say, yeah, that's electron poor, but electron poor has different meanings for different elements, and +5 has different meanings depending on what element it's assigned to. So +5 on nitrogen is much worse than a +5 on phosphorus, and so a +5 on phosphorus is not a big deal. So phosphate's not a very good oxidizer, even though it's electron poor. Phosphorus is quite electron poor, +5, right? And so what we have to do is we have to do a combination. The combination is like theory, these oxidation numbers are like the theoretical charge on it kind of thing. But in addition to the theory, yeah, we can calculate the number, but we have to assign a meaning to that number, and that's part like observation. we need to know how phosphate actually behaves. And it's not very reactive in redox. In acid base, it's a pretty decent base. Phosphate is like borderline strong base. It's right at the border there. It's almost a strong base. So phosphate's a pretty good base. Not a very good oxidizer, and a great metathesis because phosphate loves to precipitate with lots of things. Phosphate salts are quite reactive. So this reminds me. This reminds me of. So I was talking about. Why did I talk about phosphate? That's kind of because it was there. But it just brought back a memory. The memory I have is I had to take one oral exam at UCLA. And I remember the questions. One of the questions was, what are the chemical properties of phosphate? And then the chemical properties of phosphate, I couldn't answer the question because I was thinking, well, phosphate is used in laundry detergent, and that was about it. That was all about, because, the way I was taught chemical reactions was quite a bit different. It wasn't very systematic. It's like, okay, you kind of mix it with this and mix it with that and mix it with this and that and this and that and then see what it reacts with, right? And so it wasn't like, okay, a metathesis reaction is going to precipitate with all, cations other than group 1 and ammonium. For acid base, it's going to react with all acids stronger than monohydrogen phosphate, et cetera, et cetera. So now, that's one of the reasons why I thought, man, I don't really understand chemical reactions very well. And so that's why I was always interested in a more systematic approach to chemical reactions, because in Chem 4 it's not. And in Chem White, the book is not either. You read Petrucci's, I understood what they had in there, but it wasn't very good. And so finally I took a class on advanced reactions, and that was very helpful. And so that's what I'm incorporating into it. But getting back to this, phosphate is not electron rich. The oxygens are happy as is. The phosphorus is only slightly unhappy, but not really that unhappy. Was the question which of these is the most electron rich? And I gave you these choices?
There's 2 more.
Oh, okay. No wonder. Screwed it up. All right, what's oxygen here? -2. Iron? Yeah, so 3 times -2 plus 2 times x is equal to 0, the charge on this. And it is, x is equal to 3. Pretty soon you'll go, well, +3 is a common charge for iron, right? It's one of the most common charges for iron. But the interesting thing is, if you read through the chart, iron 3 is actually a pretty decent oxidizer. Iron 3 is, to put it into perspective, iron 3 is a little weaker than silver ions and a little weaker than nitrate, but it's stronger. This oxygen is not the right oxygen because this oxygen produces hydrogen peroxide, so we can kind of eliminate this one. It's a lot weaker than oxygen, but it is stronger than iodine. Iodine is a very common oxidizer. They use iodine solution to kill germs. There's copper 2, sulfate. It's stronger than acid. Iron 3 is stronger than acid, mineral acids, stage plus. So iron 3 is a pretty decent oxidizer. And so that's electron poor. And is the oxide electron rich? No, oxide is very hard to oxidize, so that's not very electron rich either. How about carbonate? So we have 3 times minus 2 plus 1 times x is equal to minus 2. What is x? Plus 4. What does the oxidation state of carbon run from? What to what? Yeah, plus 4 to minus 4. So this we consider oxygen is happy as is. Carbon is electron poor. So this would be an electron poor species. But the question is, how poor is it? And so what we do is we make a comparison. You know, the comparison's like this. This is electron poor because it has carbon in the plus 4 oxidation state. I'll just write it as Roman numeral 4. What else has carbon in the plus 4 oxidation state? Another thing that has carbon in the plus 4 oxidation state is CO2. CO2 and carbonate both have carbon in the plus 4. How electron poor is CO2? Is CO2 a good oxidizer? No, CO2 is not a very good oxidizer. And therefore, carbonate, even though it's all the way at the extreme end of positive, it's not a very good oxidizer. So did you see carbonate on the redox chart? No, we see nitrate on the redox chart. We see iodine on the redox, but we certainly don't see carbonate on the redox chart because plus 4 is not a big deal for carbon. It's like CO2. You exhale CO2 with every breath, but it's not causing any oxidative damage to your tissue. So far, we just have had electron poor species. Are there any electron rich species? So I'm just need a little bit more room to write here. So now we're at this. This is called methane, and hydrogen is assigned first, plus 1. Hydrogen usually goes first at plus 1, unless we have an alkali metal. If we have an alkali metal, that takes precedence. And then carbon is minus 4. That's, what would you say? Is that electron rich? Yeah, I'd say that's electron rich. And then based on our observations, methane is highly flammable. And it reacts with oxidizers. What do oxidizers want to do? Oxidizers want to take electrons. So what oxidizers can do is they can take electrons from carbon here. And in fact, for each carbon, it can take 8 electrons. 4 of them will take us down to 0. Another 4 will take us to positive 4. And so if we oxidize methane, we can oxidize it all the way to CO2. So we can go from negative 4 to plus 4, losing 8 electrons. So that's quite electron rich. And so fuels like this are electron rich. Lithium metal. Lithium metal is a metal. Metals are electron rich. Do you know lithium metal burns? It'll combust, just like methane. You know. Which one do you think is easier to catch on fire, methane or lithium? Maybe methane, but it's hard to call because both are highly flammable. So that's rich. All right, then let's go do this. What's this called? E. Methanol. So hydrogen gets plus 1. We do hydrogen first, and then oxygen at. Okay, and then we have 3 of these hydrogens, plus, plus. And so what is X? What is carbon? Yeah, so I got plus 1 minus 2 is minus 1. Plus 2. What is it again? Minus 3? Minus 2? Let me think. Plus 3 minus 2 is plus 2. Plus 2. I guess it's got to be minus 2. Is that correct? -2. So methanol is also highly flammable, but do you think methanol is as good of a fuel? Fuels have to supply electrons to the oxidizer, and so methanol is not as good. But it's still really good because methanol is extremely flammable. And so it's all relative. And so out of all these, which one's the most electron rich? Methane. And so we analyze it by oxidation states.
So we're just looking at the oxidation state of the carbon, or the first atom in the chemical?
No, in these particular examples, yes. The reason why is because things like oxygen, oxygen's already at -2, so that's happy as is, and then hydrogen over here is +1, that's happy as is. So we're looking at the other ones that might not be happy, and so it's not always this one that's going to dictate the first one. It could be another one, the second one. This would be a more challenging question. Which would be more electron rich? Sodium oxide or sodium sulfide? Well, what goes first? Well, alkali metals always go first. Alkali metals are going to be +1. And that means oxygen is -2. And this is +1, and this sulfur is -2. Until you go, oh, they're equal. Oxygen and sulfur are equal. So in this case, we're looking at the second element here. The sodium are happy as is. If sodium chloride, is it very reactive? Is sodium chloride a powerful oxidizer? No. Is it a powerful reducer? No. I mean, you could try to heat this stuff up and try to melt it. It just doesn't melt. It's pretty unreactive. And so we're looking at oxygen and sulfur in this case. But you go, oh, it's a tie because it's -2 versus -2. It isn't the tie. Which one is more rich? The sulfur. The sulfur is more rich. Do you know why? The sulfur is more rich because it's bigger and it's easier for an oxidizer to come along and take the electrons. Whereas oxygen is smaller and holds on to the electrons much more tightly. Sulfur doesn't hold on to the electrons nearly as tightly and can lose them easily. And so sulfides and sulfur-containing compounds are usually thought of as good reducers, electron rich. All right, does that answer the question for this particular one? All right, were there other questions?
Does number 12 on the practice test deal with nitric acid being an oxidizing acid and hydrochloric mineral acid?
Okay. Number 12. Let's take a look at number 12 here. I forgot what the question was. Okay. Right. Nitric and hydrochloric, both being strong acids, are equals in terms of chemical reactivity. Yeah, they're equals in terms of what type of chemical reactivity? They're equal in terms of Bronsted. But you're right. Nitric acid is what we call an oxidizing acid. Hydrochloric is a mineral acid. So nitric acid has this. The anion here is a stronger oxidizer than H+. Whereas in hydrochloric, the chloride isn't even an oxidizer. Chloride's a reducer, and it's a very poor reducer. Chloride's extremely stable. So if you pour like sodium chloride on your French fries, you don't have to worry about the chloride attacking you, because chloride's quite stable and happy as is. And so it's the H+ here. And so they're unequal in terms of redox. And then which one's more reactive in terms of metathesis reactions? Which one's more reactive in terms of metathesis reactions? And so this is kind of deceptive. Nitric acid is totally unreactive because all nitrates are soluble. And so since nitrates are soluble, it doesn't precipitate off with anything. The only thing is H plus will react with bases. But in that case, both of these have H plus, and both of these will react with the same bases. Whereas chloride will at least precipitate with what cations? Silver, lead, and mercury. So it's a little bit more reactive than nitric acid in terms of metathesis. So when it comes to metathesis, we usually use nitric acid because we avoid unwanted reactions, if we need to acidify things. But when it comes to redox, we try to stay away from nitric acid because nitric acid is such a powerful oxidizer. We try to use, if we need acid, we try to use something like hydrochloric acid. Chloride's quite stable. Okay, other questions?
You have another one about 18, where it talks about like a white precipitate forms when barium chloride is added to the solution. Something might be, and it gives a bunch of different options. And I know we made like barium sulfate in our lab, so like we know that one's a white precipitate. But like, how would we know, like what should we know for
is added to a solution. So we don't know what the solution contains. The solution can contain hydrogen. I mean, not hydrogen, hydroxide. If the solution contains hydroxide and we add barium, will we precipitate barium hydroxide? And so this problem is the solubility rules. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. Barium is one of the exceptions, so this will not precipitate. What if our solution contains sulfate? If our solution contains sulfate, then we'd expect to precipitate a barium sulfate. If our solution contained carbonate, we would expect to precipitate a barium carbonate because, well, we'll go back to sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. And so most sulfates are soluble, but barium sulfate is an exception. That's insoluble. It's going to precipitate. And then C and D. C and D is the carbonates and phosphates. Carbonates, phosphates, and chromates are all insoluble except for group 1 and ammonium. And so it could be C, D. And then we go to sulfides. Sulfides are all insoluble except for group 1 and group 2 and ammonium. And so this is a group 2, so that's soluble. That's one of the exceptions. And so the correct answer is B, C, and D.
And then you said there's a compound that forms a yellow precipitate.
That's the chromate.
Okay.
Yeah. Barium, this would be white, 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 white. Actually, this is not a precipitate, sorry. White, white, white. This is, the solubility of this is kind of high, so. Okay, other questions? No? All right, I need to start chapter 7. I got to get caught up again, and I'll probably do a video lecture and just catch up a little bit more. Chapter 7 deals with thermochemistry. Thermochemistry, we look at, energy and chemical and physical changes, like chemical energy, like in chemical reactions, and physical changes. And so some things are endothermic, some things are exothermic. So for example, melting ice. Melting ice is endothermic. It absorbs energy. Whereas freezing water is exothermic. We have to remove energy for that. And then there are chemical reactions that are exothermic too, like combustion. Combustion reactions are exothermic. And we have some endothermic reactions too. Do you guys remember that, exothermic and endothermic? So we're going to look at this in more detail. Here's looks like a combustion reaction, some sort of combustion, and a lot of energy is being released. So that's highly exothermic there. But we're going to look at some definitions here in the first section, and then we'll talk about heat. Like in order to melt ice, you need to add heat. In order to freeze water, you need to remove heat. Normally when we think about heat, heat transfer, when we think about heat, what is heat? You know what heat is?
Energy?
I'm sorry? Kinetic energy, right. Heat is kinetic energy. And when we have heat transfer, we're transferring kinetic energy from a hot body, which has lots of kinetic energy, to a cold body. If you take a hot body and a cold body and bring them together, the hot body is moving rapidly, the cold body is moving slowly, and then it's going to just transfer some of that kinetic energy due to collisions. And so we'll look at heats of reaction and calorimetry, work, first law of thermodynamics, applications, delta H. I don't know what the formatting didn't come out right. This capital D is supposed to be a delta, this triangle. I'm supposed to say delta R H. But. Then we'll look at fuels as sources of energy. Fuels are good reducing agents here. And then spontaneous and non-spontaneous processes. Thermodynamics is a long topic. And so one chapter of thermodynamics, this is thermodynamics part 1, is covered in Chem 1A, and then thermodynamics part 2 is covered in Chem 1B. When we're looking at this, the final section of this is spontaneous and non-spontaneous. Spontaneous reactions have a driving force. Non-spontaneous have no driving force, or the driving force is the reverse direction. And so in like this, in kind of Chem 1A, we look at this more qualitatively. In Chem 1B, we look at it more quantitatively. What is the driving force? Like a numerical value, a quantitative value on that. So the first thing we need to do is we need to define something called the system and surroundings. So that's what 7.1 is here. System and surroundings. The system is whatever you're studying. System is the object or process of interest. Object could be like a bar of gold. A process could be either physical change or chemical change. Give me some examples of physical changes. Melting. In thermodynamics, melting is given a fancy name. Do you know what we call melting in thermodynamics? Melting is called fusion. Which is kind of confusing because normally when I think about fusion, I think about nuclear fusion. I think about the sun. In the sun, small atoms fuse together to make bigger atoms. In fact, it's the nucleus of the small atoms that fuse together. And so hydrogen atoms fuse together to make a helium atom. In that process of fusion, a lot of energy is released. But this fusion isn't that fusion. You know what this fusion is? This fusion is if you take a salt and melt it, you're going to get a molten salt. And so it's a different fusion. So that's one process. Boiling.
What's the last word for the system definition?
This one?
No, on the right. Interest.
Oh, of interest, yeah. Object or process of interest. So the example would be melting. Boiling would be another example. Boiling, sometimes we call it vaporization. Processes could also be chemical in nature. So the system might be like a chemical change. Can you give me an example of a chemical change? Combustion. Combustion is a good one. Since the system is a process, once the process is over, the system disappears. The system's no longer there. And so, for example, combustion. Once you run out of fuel, you're going to have no more combustion. And once you have no more combustion, do you have any more system? No. And so, in these, once you melt all your ice, then there's no more ice to melt. And so a process has a finite lifetime. It's there and then it's done. But there's energy involved in that process. So when we melt all our ice, then we want to figure out how much energy was required for that process. Or when we combust the gasoline, we want to measure how much energy was released in that process. Objects, on the other hand, are things that have a very long life. Like, for example, a bar of gold. Let's say we had 100 grams of gold. You don't want that to have a finite lifetime. You want that to have an infinite lifetime. So if we had 100 grams of gold solid, we don't want to do anything to destroy that. So let's say I had 100 grams of gold solid at 300 degrees Celsius. If I have 100 grams of gold solid at 300 degrees Celsius, that's my system. And what I could do to my system is I could add energy. If I add energy to this, what's going to happen? It's going to get hotter. Let's say I have this object and I take away or remove energy from this, it's going to get colder. But it's still gold, hopefully, right? So if I add energy to this, I hope the gold doesn't disappear like the ice would. If I add energy and I'm adding energy to ice, eventually the ice is gone and my process is gone. Do you see the difference here between an object and a process, someone? We'll have more examples of this later. All right, so we're going to have different systems. Like, for example, here, we have a system inside the beaker here. And this is called an open system. The system is the whatever object or process of interest. And then what is the rest? The surroundings is what we consider the rest of the universe. So, have you heard of the first law of thermodynamics? The first law of thermodynamics says that energy is neither created nor destroyed. And so, if something loses energy, it just doesn't disappear, it goes somewhere. You know, so let's say I'm losing energy because I'm melting ice. I'm melting ice in the palm of my hand. I'm losing energy, but that energy doesn't disappear. The energy is going into the ice cubes, melting them. And so the energy is neither created nor destroyed. It's just exchanged. And the way we do this is we say that it's exchanged between the system and the surroundings. So this looks like it's exothermic. Do you see the steam here? And so what that means is there's energy leaking out of our system, and that energy doesn't disappear. That energy is going from the system into the surroundings. So all this out here is considered the surroundings. And then you can see the steam leaking out of the beaker. As the steam leaks out of the beaker, that means matter is going out into the surroundings as well. And we call this an open system. In an open system, energy and matter can be exchanged with the surroundings. And so there's free flow of energy and matter between the system and the surroundings. So I can input energy here, I can input matter, or I could take out energy and take out matter. It's an open system. We don't really deal with open systems because open systems are a bit complicated, or more complicated than they need to be. Most of the time we deal with closed systems. In a closed system, we don't want any matter to escape. We're going to keep all the matter there. So there's a ground glass stopper on this glass here. And so no matter can escape. However, energy can escape out of this. And so if the system loses energy, the surroundings gains that energy. And it's like this. Energy, is it possible to have negative energy? Is that possible? Well, what I'm asking is something like this. Like, if I wanted to generate, do you know the units of energy? The units are either in joules or calories. So let's say I'm on a diet. I want negative 100 calories in my diet. Can I eat something that will give me negative 100 calories? No, because I would have to consume negative how many grams of food? And can you consume negative grams of food? If you went to the supermarket and tried to buy like negative 10 grams of sugar, so that you could get negative so many calories, it just doesn't work. So what we're going to do is we're going to have a sign convention, and the sign convention is going to be like money. Let's say you have negative $10 debit on your account. That negative $10 debit means somebody else must have had a positive $10, the surroundings. And so we're going to do the same thing. If we lose energy, we're just going to give it a negative sign. It doesn't mean that there's negative energy. It just means that's the direction that the energy is lost. It's lost from whichever side you're on. If you're on the system side and you have negative energy, that means we're losing energy. And so that would be like minus $10. If you're on the opposite side, then you'd be gaining that. And so we have a sign convention for this that we'll talk about continuously. Okay, this is the closed system. Matter cannot be exchanged, but energy is freely exchanged back and forth. And then we have an isolated system. This would be like a vacuum thermos. And so if we have hot liquid in here, if this were a perfect vacuum, it would stay hot forever. Unfortunately, this is not a perfect vacuum, and it'll cool down slightly as heat leaks out. But an isolated system would be like a perfect vacuum. No energy can leak out. No energy can leak in. No matter can leak out. No matter can leak in. So sometimes we look at things that are close to an isolated system. We look inside of it. We just make sure it's well insulated from the rest of the surroundings. So, again, as far as we're concerned, the closed system is the most important for us. All right. Now, we're exchanging energy. In a closed system, we can exchange energy. We can't exchange matter. So what we're going to do is we're going to take a look at energy again. And we have something called the total energy. Total energy, we give the symbol E or the symbol U. U technically is called the internal energy. So if we want to determine the total energy, we know that total energy is made up of the sum of the E sub k. E sub k is called what? Kinetic energy, plus one other type of energy. Do you know what the other type of energy is? Potential energy. And so we'll call the potential energy PE. So the total energy is the sum of the kinetic energy plus the potential energy. And so this is just a not a drawing, but a photograph here showing this happening. So when we start out right at the beginning, what's the energy of the tennis ball up here? And let's say we just have a tennis ball sitting here, not moving. We haven't dropped it yet. And the type of energy that we're looking at is called gravitational potential energy. Because the higher the ball is, the more gravitational potential energy it has. And so in other words, we have to lift that ball up. Lifting this ball up is going to require work. And so the first thing is, let's lift this up. And so let's see how much work that's going to take. The amount of work that's required to lift that ball up, and so W is what we use for work, is equal to the force times the distance, how high up we have to lift it. And the force is equal to the mass times the acceleration. And the acceleration for us is called a G. And so it's going to be M times G times H. H would be the height or the distance that we lifted up. And do you remember what G is? Gravity. And gravity is 9.8 meters per second squared to 2 sig figs. We could go more sig figs there, but we'll just leave it at 2 sig figs. 9.8 meters per second squared. And so that's our G. And the mass we'll put in kilograms. So we have kilograms, meters per second squared, and the height will be in meters. And so we end up with these units: kilograms, meter squared per second squared. 1 kilogram meter squared per second squared is defined as 1 joule of energy. And so we can calculate how many joules of energy that tennis ball has. And the way we can calculate it is by calculating its gravitational potential energy. Back here. And so to figure out its gravitational potential energy, we take the mass of the ball in kilograms. We know g is a constant, 9.8. We could go more sig figs. And then the height. I don't know how high this is in meters. And then we can figure out its energy here. And what we say is it has a high relative energy, a relatively high gravitational potential energy, because it's all the way up here. And then as it falls down here, what happens to the gravitational potential energy? As it falls down, the gravitational potential energy decreases until we hit the ground. When we hit the ground, that's going to be the lowest gravitational potential energy we have. And so this is like this. You know, if I have a eraser up here, then yeah, I could fall down and it could hit you on the head, right? Or if this were lead brick, then that would have even more gravitational potential energy because it weighs a lot more. It's a lot heavier, its mass. Weight is force times acceleration. So anyway, as the gravitational potential energy goes down, then we know from the first law of thermodynamics, energy is neither created nor destroyed. And so where did that energy go? Because we're losing energy. Losing energy, losing energy, losing energy, and then we bottom out here. Where did all that energy go? It didn't disappear. You know where the energy went? It went to, and so as the potential energy decreases, the kinetic energy must increase. And so that energy went into kinetic energy. And so when we look at the bottom here, there's the red ball here. The red ball, we look at the total energy here. This is the total energy, which is the kinetic energy plus the potential energy. If it's hit bottom, then the potential energy would be 0. But it's bounced up a little bit, so it's got a little bit of potential energy. So that's what we see here. Mostly it is kinetic energy. Okay, then the ball travels up and then reaches the peak here and then stops. When the ball stops here at the top, then its kinetic energy is 0. So when the ball stops at the top, its kinetic energy is 0, and we've maximized its potential energy here. And then it drops down again, and this is the blue. This has blue striping here. So this is the blue stripe ball here. And we see that it's got a lot of kinetic energy again, and the potential energy is decreased. But what's going on here? It seems like we're losing, you know, the total energy seems to be decreasing. What's going on with that? Do you know why the total energy is decreasing? Yeah, some of it's being lost. You know what? Some of it's being lost to heat when it hits the ground here, and sound. Sound is mechanical, what we call mechanical work. And so it's losing energy by other routes. And so that's what we have. And so when we think about internal energy or total energy, we always have to think of the kinetic energy and the potential energy. Then we're okay. What type of system is this? Is this open system? Open system, both matter and energy are freely exchanged. Would this be open system? Is this a closed system? It turns out this is not a closed system. It's a closed system here because matter can neither go in or out. But here, in a closed system, energy's got to be able to go in and out. In this case, energy can't go in or out, and therefore this must be a isolated system. Well, we don't do much with isolated systems. To make this an open system, we don't want an open system. What do we want? We want a closed system. To make a closed system, this is good. However, this is not good. We have to have free exchange of energy. Here. So when we look at something like this is gravitational potential energy here, m times g times h. Gravitational potential energy, m times g times h. And that's the work. W is the work. That's the work required to lift it up there. And that work that's required to lift it up, we'll get the exact opposite energy if it drops back down. This is the kinetic energy. And what type of kinetic energy is this? This is what we call translational kinetic energy. Here. And if we wanted to figure out the translational kinetic energy of the tennis ball, we just have to measure its velocity. How fast is it moving? And then it's just 1/2 mu squared, where u is the velocity. So this would be for something like a tennis ball or monatomic gases. For molecules, it becomes more complex. Because in monatomic gases and tennis balls, do we have vibrational motion in the tennis ball? Are the tennis balls vibrating? Not really. The tennis balls are rotating, but it's a sphere, so it doesn't count. What counts as far as rotations go is if it's like this pen, if it's some object and it's going to have some kind of rotational moment. And so for molecules, the kinetic energy is more complicated because what it is going to be the translational kinetic energy, that is the 1/2 mu squared, plus the vibrational kinetic energy, plus the rotational kinetic energy. And so in an ideal gas, all we have is this. But in molecules, we'd have these additional terms here. And so the equation, the calculation for it's a bit more complicated if we wanted to calculate the kinetic energy for a molecule. So when we're thinking about kinetic energy, the transfer of kinetic energy is called heat. And that's the thermal energy. It's the kinetic energy associated with random molecular motion, in general proportional to temperature. It's an intensive property. So when we have heat exchange, we're just exchanging kinetic energy from a hot body to a cold body. So we're just transferring some of the kinetic energy. And so we can have energy transfers as thermal energy, and we can have energy transfers as work. We'll talk about work now. So this says internal energy. Internal energy can be transferred between system and surroundings as a result of temperature difference. That's one way. And then heat flows from hotter to colder. Temperature may change. Phase may change. We'll talk about that later. But what we're going to look at now is some examples of gravitational potential energy. This is a common example here. Let's say a person is at the top of a playground slide, and they're going to slide down. the slide. And so what we want to do is we want to figure out the total energy initial, that is the initial internal energy. If I wanted the initial internal energy of this person, what would it be? It would be the sum of its kinetic energy plus potential energy. Now, we know that this, have you seen this symbol, E bar K? What does E bar K mean? The average kinetic energy. And what is it proportional to? The average kinetic energy is proportional to the temperature. So the temperature is just a measure of the average kinetic energy. So let's say we start off at 25 degrees C. And then this person slides down the slide. The person slides down the slide, and then we have U final. U final is equal to the sum of its kinetic energy plus potential energy. All right, let's say the temperature of that day is 25 degrees C. So if the initial temperature is 25 degrees C and the final temperature is 25 degrees C, was there any change in kinetic energy? If the initial temperature were 25 and the final temperature were 25, there's no change in kinetic energy. That is, EK initial and EK final are the same. So EK initial is equal to EK final. Therefore, delta EK is equal to 0. There's no change in kinetic energy. And so what we can do is we can see what the change in energy was. So if we do delta U, that is the change in energy, which is equal to U final minus U initial, which is equal to delta EK, that is EK final minus EK initial, plus delta PE. Delta PE is PE final minus PE initial. Then we know that delta EK is equal to 0. So the only change here is the change in potential energy. And so to calculate the potential energy here, PE initial, we have two choices. PE initial will just equal mgh, so it'll be the height here. So once this person hits the ground level, then what's their potential energy? It's 0. That's what we call a relative 0. Because it is possible, once they hit the ground level, it is possible to fall down further. Let's say, they hit the ground level and they're walking, and then there's a big hole in the ground, and they fall inside the hole, then they'll be at an even lower. And it depends on how deep the hole is. The deeper the hole, the deeper they're going to fall. They're going to keep falling until they hit what? So if you could just keep digging a deeper and deeper hole, then you'll hit the absolute 0 of gravitational potential energy. And where is the absolute 0 of gravitational potential energy? The center of the Earth. And so once they hit the center of the Earth, then they'll stop falling. unless they got a lot of momentum, and then it can fall through. But anyway, here what we're going to do is we're going to set an arbitrary 0. So once they hit the ground level, there's no holes, they're down there. And so the MGH will just be the height here from the relative 0, relative ground level. And then we go over here, and then the height is 0 now, right? Because we're measuring the ground level as being 0 height, and so that's going to have 0 potential energy, relative potential energy. If we measure it from the center of the Earth, then it's not 0. That's absolute potential energy. But here, now we're at 0. And so what happened to all that energy? We had a change in potential energy. Where did it go? Where did all that energy go? You know where all that energy went? It went into, it depends. It depends on how slippery the slide is. Let's say the slide isn't terribly slippery. All that energy went into heat. And so now the slide is going to be warm. And probably the pants are going to be warm here. And that's just due to the friction. And so energy was neither created nor destroyed. That energy went into making heat. You know what symbol we use for heat? We use the symbol Q. That's heat. So in this case, we could lose energy in the form of heat. And so that's our delta PE. Our delta PE resulted in heat being generated, which is Q. What if this person didn't go down the slide? What if this person accidentally fell off the top here? They fell off the top. Are they going to generate much frictional heat with the air? No. What's going to happen is they're going to fall off here and then slam into the ground. When they slam into the ground, then they're going to make like mechanical energy. Mechanical energy might be like a scream of pain or something like that. You know, that's one way they can lose the energy. Or what could also happen is they could end up like breaking a bone. If they end up breaking a bone, that would be mechanical energy. And so they land here on the ground. And so in this case, not much heat was generated. In fact, probably no heat was generated, or maybe there was some impact heat here. Most of the energy that was lost here went into work of breaking a bone. And so we call that work here. Or we could have a combination of heat and work. Let's say somebody put a lot of oil on the slide. They put a lot of oil on the slide so that when they got to the bottom, they were still moving very fast, and then they crashed into something. And when they crashed into something, they ended up breaking a small bone. Or if they fell off the top here, they end up breaking a big bone and generating a little bit of heat at the impact site. And so what we're saying here is that when we have a loss of energy, that energy is going to be in the form of heat, that is this transfer or generation of kinetic energy, and work. Heat and or work. Okay, there's one other way of doing it. Let's say they want to do the maximum amount of work. If they want to do the maximum amount of work for something like this, then they might set it up like this. If we have the person at the top, and then this person at the top ends up tying a rope around their waist here, and then this rope is going through a frictionless pulley here. And the frictionless pulley, the rope goes all the way to the ground and is attached to a mass that weighs about what they weigh. And then they oil or grease the slide so that there's very little friction. They'll put oil or grease on the slide and then go down. But they're going to go very, very slow because this mass is about the same as the mass of the person. And so as they're going slowly down this oiled slide, they're going to generate very little heat because there just isn't much friction there. And by the time they get to the bottom, plus they have this rope pulling up the weight or the mass. Oops, it should be blue. And now we have the mass at the top, the slide. So here we have very little heat, mostly work. So the energy that was lost went somewhere. The energy that was lost went into doing work. And the work that was done is lifting up the mass. How much work was done? Well, it depends on how heavy the mass is. How many kilograms is that mass? Against G, which is 9.8 meters per second squared, and the height, how high up did you lift, and that's how much work was done. And that's going to be in joules. The units for energy, the most common units that we use are joules. And so let's go back here and just take a look at it. 1 joule is defined as 1 kilogram meter squared per second squared. So when we look at the units, whether it's kinetic energy or gravitational potential energy, the units are going to be the same. Kilograms meter squared per second squared here. And that is when we take the mass times G times H. And it gives us joules here. So I'm saying negligible heat was generated here. So Q is about equal to 0. Do chemists care much about gravity? Are we really going to be calculating gravitational potential energy? No, not at all. But you know what chemists do care about? Chemists care about chemical potential energy. So let's talk about chemical potential energy next. So let me add a blank slide here. Chemical potential energy is relative to something. So if I'm comparing, like, let's say the chemical potential energy of methane versus methanol, I'm comparing it to something. And one thing I could be comparing it to is combustion. Which of these two would you expect to have higher chemical potential energy, methane or methanol? Methane. You know, methane is a better fuel. It's more electron rich. It's more dense electron compared to methanol. And so we would say that methane has higher chemical potential energy to react more violently than methanol. Some things don't have very much chemical potential energy. So when you do a precipitation reaction, you know, I really don't worry about too much chemical potential energy because too much chemical potential energy can result in explosions. And so if you precipitate, let's say, calcium carbonate, I really wouldn't worry much about an explosion, because in metathesis reactions, we just have atoms, rearranging. So in chemical reactions, the atoms get rearranged. In acid-base, I got to worry a little bit more, because if I have a strong acid, I want to be careful. Strong acids have a higher chemical potential energy, and therefore we should adhere to the safety rule. What was the safety rule for acids? AA? Add acids. We add acids slowly because, strong acids have higher chemical potential energy, which can result in more energy being released and more violent reactions. But still, acid-base reactions aren't that violent. Still more atoms rearranging. You know what are the most violent, potentially? Redox. Redox can be the most violent. So, for example, natural gas explosions. Natural gas explosions happen every year. There was one, I think a couple of years ago, that leveled the 5-story apartment building in New York City. Did you see the news on that? No, that was from a natural gas. That has a lot of chemical potential. Methane has a lot of chemical potential energy. If we fill this room up with natural gas, would you worry? I mean, would you start to sweat, cold sweat, or? I mean, fortunately, we can detect it because natural gas has an odorant in there. They put some of the smelliest compounds in there at very, very small levels. You know what the smelliest compounds are, usually? What element they have in them? Sulfur. And so they put a thiol. I forgot which one, but it's one of the smellier ones that you can detect at the part per billion level, so they barely have to use any of it. And it gives that distinct odor of it. And so they do that because the chemical potential energy of methane and air is very dangerous, right? Very dangerous. And so we have different things with different chemical potential energies. So that's what we're looking at, chemical potential energy. Some things have high chemical potential energy. I treat, let's say, I treat a leaky gas valve, so this is dripping out methane, versus a leaky water faucet totally differently. Because, what's the chemical potential energy of water? Is it very high? No, water is very stable. It's unreactive, so it's got pretty low chemical potential energy. I mean, there's not too many things you can do with water. There are certain things you can do, but causing an explosion is not one of them usually. Would you worry about you might worry about a steam explosion. Those are very dangerous. You might worry about an implosion, like if you're in a submarine, deep underwater. You might worry about that, but those are different scenarios. And so here we're looking at chemical potential energies, like in combustion and other things. And so let's take a look at a couple of systems here. So the first system we're going to look at will just be $50 grams of water. So I'm going to have some water here, like this, and this is going to be 50.0 grams of water at 100 degrees C. What happens if we remove energy from this? If we remove energy from this, we're going to cool it down. So this is what we call our system here. Our system is the 50 grams of water at 100 degrees C. And if we cool that, we're going to get 50 grams of water at a temperature less than 100 degrees C. And so what we define for this system, a system is an object. And when a system is an object, all the objects can do is they can either warm up or cool down. That's it. So here we have an object that's 50 grams of water, and we remove energy, it just cools down. So we still have the object, we still have 50 grams of water, but now it's at a lower temperature. And so when we look at this, this is going to be U initial, which is our total energy initial. Our total energy initial is going to be equal to the sum of the initial kinetic energy plus the initial potential energy. And then we go down here to U final. Our total energy final will be equal to the kinetic energy final plus the potential energy final. And then we look at the potential energy. Did the chemical potential energy change? So we started with liquid water, we end with liquid water. How flammable is liquid water? Not very. It's very hard to strip the electrons off oxygen. It's possible, but very hard. You can't do it with oxygen, though. It'd be oxygen versus oxygen. And so the chemical potential energy is pretty low for both of these. And did the chemical potential energy change? Is it still water? Yes, it's still water. And so what we see here is that the potential energy initial and the potential energy final are equal. Therefore, no change in potential energy. So what was the change in? The change was only in kinetic energy. And what happened to the kinetic energy? If the temperature went down, the kinetic energy went down. And so the kinetic energy went down. So we lost kinetic energy. If we lose kinetic energy, then something must have gained the kinetic energy. And what gained the kinetic energy? The surroundings. The surroundings gained the kinetic energy. And am I out of time? Yeah, so we'll continue this next time.